So I was in the middle of making videos for my PyTorch tutorial series. There's a link in the description to that. And I got to a point where I had to use the cross-entropy loss function. And I was sort of thinking, oh, well, I could just give that loss function, treat it like a black box, go through it and, train some machine learning models. But that wasn't satisfactory to me because I think you really need to understand the cross-entropy function itself if you're going to be training models, and especially if you're going to be doing novel, new things in machine learning. In this video, we'll study the heck out of the cross-entropy loss function, and we'll go through examples in both image classification and also image segmentation, because this loss function shows up in both domains. If you enjoyed this video and you're new here, or maybe you've seen my videos for a while, remember to like and subscribe. Only about 50% of you are subscribed. And have fun watching. So to study this loss function, we'll go through some examples in Python. I'll use Numpy for most of them. I want this to sort of be independent of a specific machine learning library. But at the end there, we'll import Torch, and I'll show you that the way that we compute cross-entropy is the exact same as PyTorch computing it. So the best way to think about cross-entropy, it's sort of a weird loss function, but we'll consider an initial problem here. And it's a very simple problem. And the problem is, suppose I have a set of numbers, a vector p. I'll specify like this. For example, 1, 3, 5, 2. It's just a list of numbers that you have. And I have a big N of them. So it could be as long as you want. And the question is, I want to know what the corresponding matching set of numbers, another vector which I'll call q, and it has entries q1, q2, q3, and it's the same length of p. So I want to know what values do I put inside q so that the following function is minimized. And it's a function which I'll call h. It's a function of both p, these values here, and q, the unknown values. So I need to change q to make h as small as possible. And h is given by the sum of little pi times the natural logarithm of qi. And the constraint is like, you could just put the biggest values of q possible, and this is going to be small. Well, you want the constraint that the sum of the pi's is the sum of the qi's. So the sum of their values is the same. It's a constraint on the two vectors, so you can't make one super large. And so, for example, here's a sample array here. P, it's just 514624. It's just an array of 6 numbers. And we'll try out a few different arrays and see which one makes this function here as small as possible. So we'll try P itself. Of course, that's one option. And then I'll try some other arrays here with other values. And let's see what happens. So, of course, we need to import our packages. And so let's define these arrays like this. I just have P and then 3 different sample Q arrays. And in order to compute this function, it's very simple. I just take my array p times the logarithm of, for example, let's start with q1, and let's see what value it gives. So it gives negative 31.27. So that's one value. This one is negative 22, so it's not as small. So the function was smaller with q1, so it's currently minimized with this value. And I'll try q3 as well. And you see that these are both smaller than when I put q1 in. So it turns out, you can mathematically prove this, that the set of numbers that minimizes this function, you change the qi's to make this as small as possible for a fixed set of pi's here, is exactly q is equal to p. And so we can actually prove that it's the case that q has to equal to p. And this is because this is just a standard Lagrange multiplier optimization problem. You want to find the extreme values of this function here. Remember that you're changing q's, so q's are your free parameters, with the constraint that the sum of all the p's is equal to the sum of all the q's. So this is perfect for Lagrange multipliers. And so you have this function here. You define a new function f, and it's the function that you want to find the extreme values of, in our case the minimum, minus some just parameter here called lambda times the constraint. And this constraint in here is this function is equal to 0. So we have it set up for a Lagrange multiplier optimization procedure. Then what you do is you set the derivative of df with respect to all the free parameters. So the free parameters are the qi's. So df dqi is equal to 0 up here. And then also df d lambda is equal to 0. And I realize there's a mistake here. This needs to be plus lambda. And so with setting the derivative of each of the qi's, well, here it's simple. It's just minus pi over qi. The derivative of the natural logarithm is 1 over the thing inside it. And then also the derivative here, well, there's the sum of the qi's, so the derivative will hit one of these qi's, and the derivative of qi with respect to qi is just 1. So that's where you get this extra factor of lambda coming from. So df dqi is this from this whole expression here, and this is equal to 0. So this is finding the extreme values of this function here. DFD lambda is also equal to 0. Well, that just gives you the constraint back. It's the sum of the PI's equal to sum of the QI's. So from these up here, you get two equations. You get PI's equal to lambda QI from this equation, and also the sum of the PI's equal to QI's. Well, from this first relation, you can also derive that, well, take a sum here and a sum here. The sum of the PI's is equal to lambda times the sum of the QI's. And if you look at this expression here and this expression here, it can only be true if lambda is equal to 1. So therefore, QI or PI is equal to QI. So all the QI's are equal to all the PI's. The vectors are the same. And that's what you get here. So we've proven that with the cross-entropy loss function, if you have a fixed P value, the Q that is going to minimize this is going to be Q equals P. So this function is a measurement of the similarity between P and Q, and it's minimized when they're exactly the same. It's sort of like the mean squared error between two vectors. It's minimized when they're exactly the same. So cross-entropy is just a different way of saying, well, what is the difference between these vectors? And the larger the cross-entropy, the more difference there is. And then there's a minimization when they're exactly the same. So how does this relate to machine learning? And what is the cross-entropy loss function? So in classification problems, let's set up the whole sort of arena here of what goes on. So you take in an input, like an image, for example, and I'm going to call this X. X is always like the input to some machine learning function, and it spits an output. So you take in an image. It may contain, for example, one of 5 different objects. Suppose you have a dog, a cat, a house, maybe like a tree and a cloud or something. I don't know, 5 different objects. And I'm going to call the true likelihood of an image X belonging to class I, so there's one of 5 classes, as PI. So it's set up in such a way that, well, if you were to look at an image, you might know 100% that the image is a cat. So the PI is like 0000100. So you're very confident. But it's set up in such a way that maybe you're not totally confident what the image is. So your PIs don't have to be like necessarily, you know what the image is. And the goal of the classifier is to create a function f such that, so you have a function f that takes in your image X, and it predicts Q. And Q is sort of the list maybe of the 5 different possibilities. So if there's 5 different objects, then P is going to be a vector of length 5. This is going to predict a vector of length 5, and it's going to give the probability of it belonging to either dog, cat, house, whatever. And it will just give a value. So it's a probability sort of mass function in this vector. So, and the goal is that you want Q to be as close to P as possible. So if P is like 00100, where maybe the 1 corresponds to cat, then you want Q to mimic that as best as possible. So it's sort of summarized in this picture here. But the most important thing to note is that P and Q are probability mass functions. Each element of the vector corresponds to the probability that this image X belongs to a certain class. So looking at this here, so here's my vector P. And maybe P, this first element of the vector corresponds to house, then tree, then fence, then cat, then dog. And maybe you know exactly that this image is a cat. So it's not a house, not a tree, not a fence, 1, 0. The sum of this vector is equal to 1. And that's why that constraint, the sum of the PI is equal to the sum of the QI, comes in handy, because Q is also going to be a probability mass function. And you want these probability mass functions to be as close together as possible. This is a probability mass function. It's only everything is probability 0, and then cat is probability 1, because just looking at this, you know this is definitely a cat. When you know what class the image belongs to, I'm going to call it C tilde, like this. So here's like a cat. So C tilde in this case would be cat here. Then it's the case that P of C tilde for this particular class cat is equal to 1. For the class I is equal to C tilde. So C tilde is just an index like 0, 1, 2, 3, 4 of the vector. And all the other PIs are equal to 0, which is what we have here. Then you feed it into some machine learning model F. It predicts a corresponding vector Q for this image, and it gives the probability. So it's saying, oh, well, it's a 0.064 that it's a house, 0.077 that it's a tree, 0.09 that it's a fence, and 0.63, so 63% chance that it's a cat, and 14% chance it's a dog, which might happen in machine learning because, well, this looks like a cat, but a machine learning model might mistake it for a wolf or something. If it's in the snow, it's got the tree here. So your model takes it in, and you want this probabilities to be as close to this as possible. And so when you're tuning your machine learning function, you use the similarity between Q and P to optimize the parameters of your function f. But of course, that's for other machine learning videos. We just want to study the cross-entropy function specifically. So to minimize the difference between p and q, we minimize the cross-entropy loss function, which is what I showed above. And of course, this is minimized when p is equal to q, the two vectors. Now, in the case where we know which image the class belongs to, one of the pi's is equal to 1. For example, here it's cat, it's just this here, and the rest are equal to 0. So if I sum through this, well, only one of these is equal to 1, and that's when I is equal to C tilde. Remember, C tilde is the one where the probability is equal to 1. So the sum sort of is 0 for everything except for the case when I is C tilde, and I just get minus the natural logarithm Q of C tilde. So Q of C tilde in this case is 0.63 here. So let's actually look at some sample P's and Q values here. So here I'm defining an array P and an array Q, and I'm going to normalize Q so that its sum is equal to 1. And so here's my P, it's 0, 0, 0, 0, 1, 0, 0, 0, 0. So I'm saying it's the fifth object. Of course, here, this particular thing, it was the fourth object, it was cat. In this problem here, I guess I have 10 different objects, and I'm saying that it belongs to the fifth class. And Q is just a bunch of probabilities. And the sum of the P's is equal to the sum of the Q's. I know what class this belongs to, and these are all my values here. Now, if I want to evaluate this sum, well, in this case, I know that there is only one value of P, where it's not equal to 0. So I can just take H is equal to minus np.log of the Q's. So those are the Q's here, where P is greater than 0. So I'm only taking this particular spot. Remember, P is greater than 0 gives me an array that looks like this. False, 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 true. And if I index Q using this Boolean array, it will say, well, false, 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 true. So it'll take that value and it will return that value for me. I plug that into the natural logarithm and it gives me the value of H. So this is like thing here, this Q of C tilde, converting that into coding language here. It's just the equivalent to typing in the natural logarithm of Q where P is greater than 0. So note the similarities between this expression here and this expression here. It's very useful to be able to convert mathematical things you see like this into expressions on the computer in like very simple code. So what happens if we make the probability of Q higher at this point? Right here, it's like 13%. Let's actually make this higher. So I'm going to set it to a really high value. Then I'm going to renormalize Q and I'm going to evaluate H. And so if I look at Q again before we look at H, you can see that everything is really small. And now there's a very high probability that Q is the fifth class. And when I do that, you can see that the cross entropy gets much, much smaller. So by adjusting Q so that Q is a better prediction of what my image belongs to, then I minimize the cross entropy. Remember, the most important thing is that the cross entropy measures the similarity between Q and P. And entropy is chaos. So the more different they are, the more chaotic. And the smaller that value is, the smaller entropy, the more similar those two arrays are. That's sort of how the name comes about. So then the question becomes, well, what happens if I have multiple images? I want to evaluate this over n images and sum them all together. So n is the number of images that I have. I'll index these as little xn as my nth image. And suppose we know exactly what class each image belongs to. So then the true class of the nth image is C tilde of n. So I give you the nth image, so the first image, and you return an index C tilde. Remember, C tilde equals I, it was 4 here. So C tilde is just an index of the vector that lets me know what class an image belongs to. And so then the probability of image n belonging to class C, so C is just an arbitrary index of the vector, is Qn of C. Right, so Q for the nth image. Q is going to be different for every image because every image I give it, I'm going to get a different probability here. So Q depends on n. So Q little n is the Q of the nth image. And then I have all maybe 10 different classes. So I have Qn of 0 of my 0th class. What's the probability of it belonging to the 0th class? Qn of 1, the probability of the first class, second class, and I get that for each different image n. So again, going slowly, think about this. The predicted probability of image xn belonging to its true class, C tilde of n, remember C tilde is the true class of the nth image, is Qn, so that's the vector corresponding to the nth image that I feed it. And C tilde of n is the index of the true class. So for example, maybe this is my 4th image. Maybe this is Q subscript 4. And if I know that, or say it's my 3rd image, this will make it simpler. This is my 3rd image. So this vector is q subscript 3. And I know that c tilde is equal to 4 because 0, 1, 2, or yeah, say this is the first index, second, third, 4. So c tilde is equal to 4. So this would be q3, and q3 of 4 is 0.63. It's the probability of it belonging to the true class. So that's what I have here, qn c tilde of n, because c tilde also depends on which image it is. And summing this together, well, I'm going to sum all the h's together to get my loss function L. L depends on P, the true probability, and Q, the probability that I'm predicting. I sum all over all the different images of my H's, and I just get this sum here. So let's actually compute it for some values. So here I'm going to make an array of P's like this. It's a 2D array, and there's 10 different possible classes that each image can belong to, and I have 4 different images. So this is my P for my first image, and it belongs to the 5th class. This is the P for the second image. Maybe it's a picture of a moose. Belongs to the 3rd class. So 3rd class might be moose. The P for the 4th image and the 3rd image and the 4th image. So they all belong to different classes. And well, I already showed it up here, but yeah, this is what P looks like. And so then we can get a probability of array, just a sample probability or array of the Qs. So we'll get the Qs and then we'll normalize them as follows. So these are my Qs for my first image. There's going to be 10 of them, and it gives the probability of it belonging to a certain class. Same with the second, third, and 4th. So these are the true things that it belongs to, and this is maybe some machine learning function I have. It computes the probabilities, and so I have an array of Q for each image, and there's 10 different classes. So now we can compute H for each term, and the way I do that is the same as before. I take my Qs, which of course is going to be a 2D array, but I want them where P is greater than 0. So it's going to index them at this location, this location, this location, and this location, because all the other P's are equal to 0. So it's only taking the natural logarithm at the locations of my true class C tilde, because this gives the index of C tilde as well. And so here's my P's, and I take Q where P is greater than 0, so it will take, 0, 1, 2, 3, 4, 5, so it'll take 1, 2, 3, 4, 5, it'll take like natural log of this value plus the natural log of this value, and the same thing for the last 2 arrays as well. So this is a very simple way of indexing it. So there should be 4 different values because I have 4 different images. There's 4 different true classes, and as I'm summing from n equals 1 to 4. So I'm taking the natural logarithm of 4 different things here, and I get, Q where P is greater than 0. These are the Qs. I take the natural logarithm of these Qs to get my array of H's, which is also going to be an array of size 4, like this. Just taking the natural log of, or the negative natural log of each of these values, and then L is just the sum of these, and I get my cross-entropy. So in machine learning, it can be a little complicated sometimes. We know that Q should be related to a probability density function, and in the examples above, I'm sort of normalizing the Qs to enforce the constraint that Q is a probability mass function. But so they're bounded between 0 and 1. The closer that each element of the Q is to 0, the less likely we are confident that the image n is class C. And the closer to 1, the more likely we are confident that image n is class C. So I take my nth image and I look at these numbers, and the small numbers say I'm not confident it's that class, and the larger numbers close to 1, I am confident. And the most important thing is that if I sum all the Qs together for a particular image, it equals 1. And so this is the normalization constraint. And suppose a neural network outputs f of xn is yn hat, where yn hat is the same length as the number of classes. So maybe it's 5 classes, yn is a vector of length 5, but yn is not normalized because neural networks don't necessarily normalize in their output. And so we can enforce the last condition. This is one way to normalize. I was normalizing a different way above, by dividing by the sum of the Qs for each of the different arrays here. That's one way to normalize. So like, for example, I treat this as a vector, and then I divide all of these by the sum of all these values, and that will normalize. That's one way to do it. In PyTorch and most machine learning libraries, the way it's done is as follows, and it's sort of based on statistical mechanics in physics. And so the way that they normalize to get the Qs is they say, okay, Qn of C is going to be, so there's C, remember, is the index of the class. It's the index of the vector. Q is a vector, maybe 5 elements, so there's 5 different values of C. I take the exponent of yn hat of C. This is just a number. It's the nth image. C. So y hat is also a vector. So for each image, I have a vector of maybe length 5. So C specifies what index I am. And then I divide by the sum of the exponents of all those different things. And so this will make it so that each Qn is normalized, because if I sum this over all the different classes, I just get the sum of a numerator over all the different classes divided by the sum of the denominator over all the different classes, and that's equal to 1. You can prove that. If I take a sum here of C prime equals 0 to C, that goes to the numerator, and Q is just a normalized vector. So our loss function is now expressed as follows. It's L of y hat. So it's the function of the prediction of the network. It's this sum here, which I specified before. I sub in Qn of C, like this. Remember that I have a C tilde here. I plug this in, so this expression into here, and I get this expression here. And this is the cross-entropy loss that you see when you look at the PyTorch documentation. And it's a little bit non-intuitive when you see it, but you can tell now, based on what I've said, of what they're doing is they're taking these general outputs of the neural network, y hat, they're normalizing them to get these vectors Q using this particular normalization procedure where you use exponents. For example, if you were to do it without using exponents, the way I did it would just be not having exponent here or here and just taking y hat of C divided by the sum of y hat of C. But they put an exponent there because it helps. And so this is your cross-entropy loss function. And so for a given n, y hat is the network output for an image xn. So this is just reminding you that n is the image index and C is the class index. So here's a sample y hat, for example, and I can look at it, and it's just, a bunch of different values. So here it's 4 by 10, so there's 4 different images, 10 different possible classes per image, so it gives a probability. But of course, these aren't normalized to equal 1. And the shape is 4 by 10, 4 image, 10 different classes per image. And then we compute the Qs using this expression here. And for that, well, I do 2 different things. First, I take the exponent of the y hat to get a Q that's even larger. So now these are all sort of exponents. And then I normalize each of these so that they're equal to 1, which is exactly what this expression does here. It takes the exponent of all the yn hats, so that's what I first do, and then it normalizes so that each of the 10 classes per image, the probability is equal to 1 when you sum them all together. So I need to normalize this so it's equal to 1, this so it's equal to 1, this so it's equal to 1, this so it's equal to 1. And the way I do that is, well, I sum the Qs, so Q is 4 by 10. I sum over this axis, so that gives the sum across rows. So this might be like 15, 14, 13, 12, for example. That's what this will give. So there should be 4 different values. If I look at this expression here, it's the sum of each of the different rows, and I need to divide each row by the corresponding normalization factor so that each of them are normalized. Now, the shape of this array is 4, comma, and the shape of this array is 4, comma, 10. So in order to divide this array by the normalization factors, I need this array to be 4 by 1. The way to do that is to expand the dimensions like this. And now I look at the shape, and now it's 4 by 1. Now these two shapes, 4 by 1 and 4 by 10, are compatible. The Numpy broadcasting rules. So I first take the exponent of all the y hats. That's what's being done here. And then I normalize rows. That's exactly what's being done here. And so I get the exponents, and then I normalize. And if I sum across the rows, each of the sum of the rows is equal to 1, and that's exactly what we want. This code isn't trivial, by the way. I would take a moment to look at it and really think about what's going on, but we've normalized the Qs using this procedure up here. Then I compute C tilde of n, so I call it C squiggle here. And C squiggle says, okay, so for the first image, so image with index 0, C is equal to 4, so it's the 4th class. For image with index 1, it's the 2nd class. For index 2, it's the 8th class. For index 3, it's the 6th class. And that's just can be observed by looking at P. So for the 0th image, it's the 4th class, where, of course, class 0, class 1, class 2, class 3, class 4. And it gives it for each one of these. Then I can index the Qs, which I now have like this. using this C squiggle. So I index Q using C squiggle. It should give me 4 different values. So I'm summing across images like this. I take the natural log and I sum them together and I get my L like this, and it's 41.827. And so in PyTorch, of course, you would do it like this. So you define your cross-entropy loss function. Here you're going to sum across different images. That's why I put reduction equals to sum. And I can evaluate on our data above. So here's the y hat. This is the unnormalized y hat. And I also have p, which is the array basically of the true values here. And I plug them in and I get the exact same value that I have above. So this is the inner workings of the PyTorch cross-entropy loss function. Before I finish this video, I also want to talk about image segmentation, because this is another area where the cross-entropy loss function is so important. And so suppose I have this image of this cat here, and I want to segment the image into 3 distinct regions: cat, couch, and then background. So there's 3 different regions. And so for each pixel in the image now, I'm going to define a vector p. So vector p is equal to 1, 0, 0 is background, p is 0, 1, 0 is couch, and p is 0, 0, 1 is cat. So each pixel has its own vector, and the vector corresponds to which class it is. So now, above we were summing over different images. Now we're going to take a single image and sum over different pixels to compute our total cross-entropy loss function for our prediction of segmented regions in the image. So for each pixel, we also have a corresponding value of Q, which is the probability that the pixel is one of the 3 objects. So you're determining for each pixel, what object does that pixel belong to? And then we sum over pixels. So N, capital N now is the total number of pixels in the image. So we sum over every pixel in the image and we take Qn of C tilde of N. Remember that this expression here says, give me the value of Q corresponding to what class it corresponds to. So for example, if P was equal to 0, 0, 1, then C tilde is equal to index 2. Remember, index 0, index 1, index 2. So C tilde is equal to 2. And then I only take the natural logarithm of Q, the second index of Q, so the last element of Q. And I do that for all the different pixels depending on what the values of P are. Of course, then I normalize also the QNs with the output YN hat, like I did above as well. So we'll load P here and we'll plot, and I'll sort of describe what this means. So here's all the pixels in the image. And what I'm doing here, for example, this first plot, is I'm plotting this thing here. And so this says, give me the first element of the vector P for all the different pixels. So the first element is 1 here. This is the background, and 0. Remember, the second element of P is the couch. So it's 0 everywhere except for the locations of the couch. So that's this yellow region here corresponding to the couch in this image. And then the third element of P, which is cat. So these are all the cat pixels, 0 outside the cat and 1 inside the cat. Now let's load Y hat. So these might be a prediction of some neural network. And of course, it's going to be a little bit fuzzy and maybe a little bit blurred at the edges. And I do the same thing. I take element 0, element 1, and element 2. And this is non-normalized. So the first thing we do is the exact same thing as before. I normalize to get Q. I compute C squiggle by taking np.where of P. This will give me the, if I just look at this. And so for example, what this tells me is that pixel 0, 0, take the first element of P. At pixel 0, 1, take the first element of P. Remember, P is just a vector of length 3 for each pixel. And then for example, at pixel 399, 399, take the 0th element of P. These 2 arrays specify which pixel I'm at in my array, and this specifies what value of P to take. Then I can index Q using C squiggle, like I did before, to get my different H's. There's going to be 400 times 400 different H's now, and I can show you that. So here I compute my H's. And so there should be 16,000 different H's, and I sum them together to get my loss. And this is my loss, and it's a very large value. And again, I can compare this to PyTorch. Here I'm taking in, remember, y hat is a image, and P is also an image here, and I get the same loss function. So I hope you enjoyed this video. I hope it gives a better description of what cross-entropy is. If you like this video, remember to subscribe, join the Discord server, all that's in the description, and I'll see you next time.